let's make a start. Today for this session we'll cover 9E and 9F. 9E is the chain rule. Hopefully you already done it and you'll be fine or not. And 9F, and I just blank out. I'm not too sure what's 9F about. It will be about derivative. Yes, now I remember. It's the derivative of a polynomial function, but the power will be a rational number, not just an integer. And you'll go, there's two ways it will be done to differentiate. The first one is using the first principles. So it's just again to review how to use the first principles, but in general you will just use the formula. Okay, but it's important that you understand how to do it using the first principle. It's about manipulating algebraic expression, simplifying fractions, and using limits. Okay, so starting with 9E, it's the chain rule. So you will have two functions. Both of them will be differentiable. Differentiable again means the derivative is continuous. So you will start with uh, g is differentiable at x, which is your first function, and f will be differentiable at g of x, so that will be your second function. So when you create a composite function, which is a function of a function, which we call q. It's a function f of g. So you start with your variable x, you apply your g function, and then you apply your f function. Now we're going to look at that derivative, and it follows um, the chain rule. So the derivative of q, which is q prime of x, it follows that rule. So you would differentiate f and in terms of g of x, and then you multiply, so it's outside the product. You have two factors, and the second factor is the derivative of your first function, so it's g prime of x. So g prime of x is the derivative of the first function, and the f prime is the derivative of the second function, and you substitute g of x, so it's not x here. Using a slightly different notation, so it gives you a more compact formula, but it's exactly the same idea. It's what we call the Leibniz notation. The first function is g of x. We're going to rename it u, and the second function f, it's going to be in terms of u because we rename g by u. We're going to call it y. So the left hand side is q prime. We're going to call it the derivative in terms of x. And what we do is we're introducing a temporary function, which is u and u. The idea is, it's the same idea as having a product of two fractions, and we're introducing a common equivalent term, and we're going to call it u. So du over du, it's the same idea. When you have an equivalent fraction, you introduce let's say a 3 over 3 that equals to 1. It is the same idea here. Okay, so the going back to the first notation, the derivative of the first function is du over dx, which is our g of x. So that g prime is equivalent to that du over dx. Let me see if I can add a bit of color just to show you. So this bit here is the same as this one, okay, by using that substitution. And that dy over du, it's the derivative of f in terms of u. Okay, now just be careful when you do that substitution u equal g of x. When you differentiate that first factor, it's going to be in terms of u, so your final expression needs to go back in terms of x. So that function in terms of u, you're going to have to use substitute u again by g of x, so you get a whole expression in terms of x, not just a mix of u and x. Okay, I'll do two examples. Alright, so the again, those slides, that PowerPoint is also, it's on Compass and on LMS. That video I'll upload it as well for your reference. So let's say look at this example. I want to differentiate y equals, it's a bracket squared of 2x to the power of negative 3 minus 4x. Let me see which notation they're using. That's fine. So I'm going to use, yeah. So the first function inside the bracket is your g of x, so that's the expression 2x to the power of negative 3 minus 4, and the second function f, it's going to be a square. So we define that composite function and we apply the formula. So before you do that, before you apply the formula, which is that one, it's as we define f here and g, just differentiate those two in terms of x. So the derivative of f gives you f prime. So you start with x squared, that gives you 2x. Okay? And your g of x, which is here, you differentiate, that gives you your g prime. So you use the polynomial rule to differentiate. So 2x to the power of negative 3, that negative 3 becomes a factor, so 2 times negative 3 gives you negative 6, and that power negative 3, you take away 1, that gives you negative 4. Here you do the same, but if you do remember, it's a shortcut. When you have a linear function, it's just the coefficient, so that's negative 4. So here you have your g prime of x and your f prime. So you apply the chain rule, just use the formula. The first factor is f prime, so that's f prime, that's 2 times x. But when you apply that, let me use a different color. So that 2x, which is the same as this one, this time instead of having f prime of x, you're going to change that x into g of x. So you have that 2 here, but instead of having x, you need to substitute g of x, and g of x is defined up here. Okay, so your g prime, your f prime of g of x, it's going to be 2 times g of x, so it's 2 times, and you replace g of x by the function here. And on the right hand side, the last factor, which is g prime of x, is just that expression. So it's going to be bracket negative 6x to the power of negative 4 minus 4. You expand, so expand the factor 2 to the first expression, and here it's a binomial expansion. We expand all of that and we regroup the like terms. Okay, so that's using the chain rule. Now you don't always have to expand it. You'll find out later on sometimes what we want to find is the stationary point of inflection. So for example, what I meant is we want to find when the derivative is equal 0. So when you have a parabola, you're looking at the turning point, so the derivative is equal 0. So if it's expanded, it's equal 0. It's a little bit hard to determine. You will have to go backwards and factorize. So usually when it's fully factorized, I would stop here and you will investigate the values of x when that is equals 0, just at that level. Okay? But for 9e, for the purpose of this exercise, they will have you use the chain rule and you will expand it to get a fully expanded answer, and you will be able to uh, uh, com- uh, make it equal, compare with the answers at the back of the textbook. Okay? Alright, so using the same example, this time you're using the Leibniz notation. So it's the same function. Your first function, alright, if I go back, when the derivative equals 0, so your function will be a sort of, it's a mix of hyperbolas. So your function, let's say we do something, I don't know, let's just do something like that. Okay? When the derivative is equal to 0, you will look at the point right here. There's a turning point here. So when you solve it equals 0, that x value that you read, it will be solving this equation equals 0. Okay? I hope it answers the question. Not in this chapter. I don't really want to do. Yes, I'll do another example. Sorry, there's a few. 1, 2, 3. I do the same example using the Leibniz rule, and then I do another example using the both formulae. Okay. So using the same function, I'm going to use a different notation. The answer should be exactly the same when you expand it. Okay. So using the same function, you have your first function inside the square. That's what we're going to call u. Okay, so this bit inside, we're going to call it u. Okay, and now the second function, after I substitute, so that's my u, and if I substitute that by u, that function y, so that function y here, which is the same as this one, it's going to be a square, but now the inside of the bracket, we're going to substitute into a u. So now that function y is a function of u. Okay, so we remove the x variable temporarily. So we remove the x variable, we'll differentiate that in terms of u, and we'll substitute back again. Okay, so let's go back to that u function, which is in terms of x. We'll differentiate in terms of x. So we do the derivative of u in terms of x. So we look at every term, they are polynomials, we differentiate, that gives you this expression. Okay, so that's the derivative of u in terms of x. Now we're going to differentiate u in terms of y. So dy over du. So because it's in terms of u, it's just a quadratic, so it's u squared, and that gives you 2u. So the 2 comes from the power, the new power with minus 1, that gives you 1, so you get a 1 here. Okay? So now we want to find out is, going back to the composite function, that y function, we want to find the derivative in terms of x, so it's dy over dx, and what we do, we introduce a temporary variable du. Okay, and now the dy over du we already calculated here, so that's coming from here, and the second term du over dx, it's coming from over here. Okay, so the left hand side, dy over du is 2u times that expression here, so negative 6x to the power of negative 4 minus 4. So that's the same, let me separate, so that looks that doesn't change, that doesn't change, that doesn't change. Now the dy over du, which is a 2u to the power of 1, that's 2u. Again, it's in a function, it's in terms of u. We defined originally u as a function in terms of x. We substitute the u in terms of x here. We expand the 2, and that gives me the same expression as what we had before. No, you do not have to expand. The only reason to expand is for you to practice expanding expression. Again, in terms of when you want to study a function and looking at the rate of change of the derivative, you actually would just leave it factorized, and you will investigate when it is equal 0. Okay, so it's actually more beneficial to leave it factorized. Okay, now Carly, I suspect you're asking about this. Now it's not a dash, it's a power of 1 that's coming from that 2 minus 1. So let me remove that. Probably I just do. So it's actually u to the power of 1. It's coming from that power of 2, and we minus 1 because we differentiate. So if we were to expand that, you will do a binomial expansion. You multiply every term by the other one, and you will regroup the like term. So you notice the terms in terms of negative 3 are common. They will regroup over here, and that will be your expanded form. Okay, but again, yeah, unless it's asking you to expand it, it's better to leave it factorized. Okay, I'll do one last example using both methods or both notation, and then I'll move on to 9f. So it's example 21, it's from your textbook. So you have your g function inside the bracket, your f function is to the power of negative 1, so it's a composite function. So using the okay, so here we'll start with the Leibniz notation. The u is what you have inside your bracket, so that's your 4x cubed minus 5x. Okay, so now your y, which is here, will be a function in terms of u. So it will be u to the power of negative 2. And what we'll do in the next step, this is a function in terms of x, so we'll differentiate in terms of x. And this one is just in terms of u, we'll differentiate in terms of u. Okay, so dy over du is on the next line here. So negative, it's u to the power of negative 2, it's a polynomial, so you need to refer again to the previous part. So negative 2 becomes a factor over here, okay? And when you do negative 2 minus 1 to find a new power, negative 2 minus 1 gives you negative 3, okay? Then the first one, which is u in terms, it's a function of x, we differentiate in terms of x, so 4x cubed will become, that's 4 times 3, and the new power will become 3 minus 1, which is 2. 4 times 3 times x to the power of 2 gives you 12x squared, and the negative 5x just leaves you negative 5. Okay? Then the product of the two is by introducing du here on the denominator and du on the numerator. So on the next slide you have that. So dy over dx, we introduce du. Okay, du over du is 1. Dy over dx coming from the left, so it's negative 2u to the power of negative 3. Okay, I need a laser pointer, that would be better. By the way, can you all see the screen? Let me actually share my screen, that might help you. That'd be better for you to visualize. I just need to open the chat on my side, and I need the attendance as well. Hang on, I don't need the participants. I just need. Again, I'm trying to manage my two screens, and it's not that easy. I don't have a lot of room. All right. Um, so here you introduce the du. Um, if y was a linear function, it will be the gradient. But y can generally be any kind of curve, so it's not necessarily an instant value. It's a function. It will change over time. Okay, so if y, for example, is x cubed, the derivative of x cubed is 3x squared. Now you can see that dy over dx will be 3x squared. That's not just a gradient. It's a function. If you substitute x with a specific value, so you take a snapshot along the curve and you pick a specific value of x, then the dy over dx will have a value, then it will become the gradient of the tangent. Alright, so continuing with this, you have your negative 2u negative 3. You go back to your original definition of u, you will substitute back into here. On the right you have your du over dx, which is your expression that you calculate over here, okay, and that you substitute into here, which is hang on, which is that one. But what it did is the power of negative 3 you had over here, they turn it into a positive, so that becomes the denominator. Okay, so it's a nice factorized form. Just leave it factorized. Okay, and that's using the Leibniz method. Okay, so we'll still use the same function where we use a different kind of substitution. Let me see if that works. Okay, so you have your the first and the second function. Here they will use a different letters. So function f, which is my y, is g of h. H is the first function. So you have two functions in terms of x. You define h and g. You differentiate both of them in terms of x. Okay. With the second function, which is your g, when you differentiate, when you're going to introduce the chain rule, that derivative, so you have your g prime here, you need to substitute x by h. Okay, so that's the definition. So that's what you need to be doing. So the first factor you differentiate as g prime, you substitute your x by h. So here that is your g prime in terms of x. So that will be negative 2 bracket, which is your x, in terms of negative 3. You substitute h. Your second factor is just the derivative of h. So it's that expression 12x squared minus 5. You rewrite it over here. Okay. With the first factor, when you have h here, we substitute by its expression in terms of x, and they rearrange it into one fraction with positive power, and you end up with the same expression as the previous answer using the Leibniz notation. Okay. So hopefully that gives you enough information regarding the chain rule. Again, up to you. You need to use either your f and g notation for two functions. Here they use h and g, or you can use the Leibniz notation. Okay. Yeah. Before I move on, you can also use that, calculate that using the CAS calculator. So it's a good idea. You use the define function. The ability to do that is you define your first two function g of h, and then you define your composite function by giving it a new name, and you make it a function of a function. Okay, and then you will set your derivative in terms of for the function f in terms of x, and it will give you the same answer. So you do, those are a little bit of screenshots. So you define your function. So you define your two functions that make up your composite. You define your composite function. Then you go to find the derivative. Define is probably the same as storing. Obviously, if you have a multiple choice question and you're in a hurry, in the second exam, just use your CAS. Also, the only reason you will define is if you have a problem that has multiple parts and that we require to use the same function, either the derivative or the original function for let's say intercepts, asymptotes, or the graphing of it. The fact that you define it, you can reuse it in different tabs. So you'll have your calc tab, and you can also create a graph tab, and you will be able to recall your functions that you define. So f, g, h, and f. So here's your derivative. You define your derivative of f of x in terms of x, and you end up with the same answer. Okay? If the answer is factorized, you can also use the expand function that will expand it and will regroup the like terms. That's typically you would do that is because sometimes the answers in the textbook will have a certain format, and you want to match that format. You have a factorized form, but you're not sure if it matches the expanded form. You can use your CAS to do that. Another trick I'd like to do, and let's say I'm in a hurry, I would just substitute an x value. So let's say I substitute x equals 2, 1 or 2, and it matches the same as the answer of the back of the textbook, and then I'm fine, it's kind of correct, and I just move on. Alright, last bit for today, 9f. So we're going to look at the derivative of a rational power function. Okay, two parts. The first part is using the first principle. It's very heavy. You won't be asked to do that all the time. Okay, but it's also, it works as a proofing, and it's also for you to kind of manipulate fractional functions and also limits. So let's look at a simple function which is x to the power of 1 over 2, which is a square root of x. Just be mindful about the domain. So using the first principles, what we do is we create 2 points. So the first point is x, f of x, and the second point is slightly on the right, is you add h, so it's going to be x plus h, and the y coordinate will be f of x plus h. So f of x is the y coordinate of the first point. The f of x plus h is the y coordinate of the second point. And when you do the difference of the y coordinates, and when you do the difference of the x coordinates, that simplifies down to h. So just a reminder that h on the denominator is x plus h minus x. So the x the x's cancel out on the denominator, that leaves you h. So you will write that in that format, and the way it is at the moment, there's no way you can simplify. The idea is you want to try to simplify your h, because when you turn that into a limit, remember h converges towards 0. If you have a denominator that converges towards 0, you have no idea how that expression is going to behave. Is it going to converge toward 0, infinity, or here x is a constant, so does it converge towards a certain value of x? You're not too sure. Now, when you have a sum or difference of square root, there's a little bit of a trick that you're going to be using. Is you need to think difference of two squares. So to do a difference of two squares, here this is a minus. We need to multiply that by a sum, which is kind of the complementary in terms of difference of two squares. They are the two factors. So we allow to multiply a fraction. Okay. What do you need to annotate? Yes, Abdullah, you requested to annotate, so
Yes, sorry, so by mistake.
okay. So can I remove you then? That's fine.
Yes.
I wish I knew how. It's probably here. The annotate. I think I stopped. Yeah. Okay. So here you introduce the complementary here on the numerator and the denominator, and on when you look at the denominator, just look at the denominator and tell me what happens when you do a limit when h converges towards 0. What happens to that denominator? Again, I repeat, when h converges towards 0, what happens to that denominator here that I'm underlining? Correct. So that h can become 0. So you get a root x plus root x, and that gives you 2 root x. So now it's in terms of x, it's not 0, so it's actually the sum is not a problem. Okay? So let's continue with that. So now we're going to look at the two numerators, and we're going to combine together using a formula in. I'm going to move. It's not what I want to do. What I want to do is I want to go back to here. Okay? So you apply the formula, which is a difference of two squares. So if I use a pen, hopefully you'll remember what the difference of two square is. So when you have bracket a minus b bracket a plus b, that expanded form is a squared minus b squared. Okay, so the a term is, that's root of x plus h. When you square it, that's x plus h. The b here, when you square it, that gives you x. So that is my a squared minus b squared. Okay, the x will cancel out. Okay, as the x cancel out, you notice that you have a h over h factor that cancels out as well. Okay, now what's left is the nice sum on the denominator. I already asked you what happens when you do a limit. So now you have that gradient. You're going to apply the limit when h converges towards 0. That will give you the definition of the derivative. So the definition of the derivative here, using the first principles, is limit of h converge towards 0 of that expression that we simplified down here. Okay? When h converges towards 0, that equals to 1 over 2 root x. Okay? Now, if I write it as a negative power, it's x to the power of negative 1 over 2. and that will fit that general polynomial expression that we encountered before with the a positive or negative integer. Okay, so if your function is x to the power of r, and r being a rational number, the derivative is you multiply by let me move that. You multiply by r, and the new power, the second factor in terms of x, is r minus 1. You take away 1 from that power. Okay, even if it is a rational power. Okay, so that's using the first principles. So if it doesn't ask you to use the first principles, you will just move on to using the formula. So there's different ways of that is rewritten, but it's what I just said before. Okay, so let me move down to, so when you have a formula that includes a root notation, you need to turn it back into a fractional power. So the q root here is your denominator of your rational power. Okay, so over here, and that's what you would do over here. So this is an example. So it's f of x is 3 over root x. Root x will be x to the power of 1 over 2 with a negative. Okay, and you will just apply the rule. So that negative 1 over 2 will become a factor. Why is it gone? I think there's a mistake here. Yes, I think it's a mistake. It's missing a negative here. Let me fix that. Can I fix that quickly? Wait. Alright, let me unshare because somehow my PowerPoint stopped. Yep, I just killed my PowerPoint. Where was I? This one. Alright, so you have your function. What's happening? So you have your function here, you differentiate, the power is negative 1 over 2, that becomes a factor here, negative 1 over 2, and the new power is negative 1 over 2 minus 1. You simplify that fraction as negative 3 over 2, and that's your negative 3 over 2 factor. Incidentally, they're the same. It's not why it's happening, it's just because you have negative over 2 times 3, that gives you sort of incidentally the same. The factors and the coefficient are the same. Alright, let's do a few more examples. Okay, so with here, with those two examples, so they have rational power. So with the first one, they're already in a rational form, so you apply the formula, okay, and you do that for each term. Alright, so you want to differentiate that. The 2 becomes a factor, so that's going to be a 2 outside. You have a x to the power, it's negative 1 over 5, that becomes your factor, so negative 1 over 5. And I think I'm in the way, am I? Let me move. So you have your negative 1 over 5 here, is going to be your factor. That the new power is negative 1 over 5, take away 1. That will simplify to negative 6 over 5. You look at the second term. You have a 3 factor that doesn't change. There's a 3 here. the power is 2 over 7, that will become a factor. You do 2 over 7 minus 7, so that gives you negative 5 over 7. So the power goes down for both terms, okay? So don't be puzzled with the fact that it's fractional, that it's negative. Just do take away 1. Do the fractional operations properly. You end up with those new powers. You regroup the coefficients together and try to simplify if needed. And that is your derivative. Okay? With the second one, you have a cubic root. So you need to turn that into a fractional power. Now, what you have inside is you have x squared plus 2x. So it's going back to 9e. Is a function of a function. You need to you need to use a chain rule. Okay? So it's combining 9e and 9f all together. So here with that second example, you want to find the derivative. So that is your function here. So it's to the power of 1 over 3. Let me try to do that using the Leibniz notation. So what we're going to do is, if I call can I just actually do that on paper? I'll do that on paper because I don't think I can do that properly. So here, maybe here, somewhere here. Alright, so here what I'll do is I'm gonna call u is x squared plus 2x, okay, and y is just gonna be u to the power of 1 over 3, or the cubic root. Can you all see that? Okay, so now I'm going to differentiate u in terms of x. So that gives me 2x plus 2. Okay, and the y, it's a function of u. So I'm going to differentiate in terms of u. So it's going to be dy over du. Okay, and that's just 1/3 of u to the power of 1/3 minus 1. 1/3 minus 1 is negative 2/3. So it's 1/3 u to the power of negative 2/3. Alright, so going back to the actual question, which is, if I move my mouse, so it's that one. So that's my function y, and it's in terms of x. So I want to find dy in terms of x. Using the Leibniz notation is dy over du times du over dx. Dy over du, we find it over here. Du over dx, it's already calculated over there. So I'm going to write dy over du, it's 1/3 of u to the power of negative 2 over 3 times du over dx is 2x plus 2. Okay? And now, remember that dy over dx, it needs to be a function of x. So we have a u here. We define u to be that expression in terms of x. So I need to substitute u by this expression. So that gives me 1/3. U is x squared plus 2x to the power of negative 2/3 times 2x plus 2. Okay? So that's your derivative in terms of x. So let me go back to the example. I'll take a screenshot of that and I'll throw it into Discord. It's just another example again about f of g function using the Leibniz notation. Alright, so you have your derivative here. Okay, that negative power, they turn it back into a positive power. The denominator of the fraction, they turn it back into a cubic root. So that is the derivative. Okay? I think that's it. I think I don't have any more. Yep. So that's it for me. I'll stop the recording now.